continuing with an invited speaker. So today we have Antti Honkela here. He's going to talk about differential privacy and Bayesian learning. Look forward to this talk.
Okay, thanks. So first I'd like to thank the organizers for the invitation, and I'd like to use the opportunity to give a slightly more general talk about privacy, because I believe that has many interesting connections to Bayesian inference, and that this audience community would have a lot to give to developing practical tools for differential private machine learning. So why do we care about privacy? As individuals, people may have different views of how important they think that their privacy is. But as a society, I think it's interesting that one of the foundational documents of the sort of global constitution, the Universal Declaration of Human Rights, has a pretty strong statement, basically saying that no one shall be subjected to arbitrary interference with his privacy. So, and that there should be protections against such interference. So, as a society, we should give people a possibility to have privacy. On a more practical level, there's of course many applications where it's important to handle the data in machine learning in a privacy-aware manner. So the application that got me started into this was to personalized medicine, where clearly there's a bottleneck that we don't have enough data, and one of the reasons for that is that there's big privacy issues with the data, so it just can't be shared like that. Even if you're not working on medical data, if you are working on any data that has some personal information of Europeans, you should be aware of the upcoming European General Data Protection Regulation, GDPR for short, that will be coming to force next May, which sets very strict conditions on how you can use private information. And the definition of private information in that regulation is extremely broad, so it's basically anything that can be linked back to an individual. And so this is a European thing, but it also covers anyone who is using data about Europeans, also internationally. And there's really huge fines for breaches in this privacy, defined as a percentage of global revenue for a company. So it can really run into tens of millions. And also, kind of doing machine learning, you may think that, okay, you're doing your model, how could that breach anyone's privacy? But really, many of the models that we do retain a lot of private information. And so if you have a deep learning model, for instance, you can, from the trained model, you can separate which samples were part of the training set, what was the label of that particular sample, and that can reveal some information that maybe should have been private. So there's this term called model inversion attack for this kind of idea that you try to find out the training data back from the trained model. And in general, I guess there's a long history teaching that you can try simple methods to protect the privacy, but in the long term, they often are broken, so we would like to have some strong theoretical guarantees instead. And the best strong theoretical guarantee that we know about is called differential privacy, introduced by Cynthia Kwok and colleagues about 10 years ago, which basically says that a stochastic algorithm operating on a data set is epsilon differentially private if for any two neighboring data sets that differ by one sample, the probabilities of obtaining any specific outcome are very close to each other. So it's basically the ratio of probabilities is bounded, and because this is symmetric, then the end result is that they have to be very close to each other. And so this gives you this different privacy, or DP for short. And actually looking at the posters, I realized that for some of you, DP might stand for digital process, but I will be using it for differential privacy here. So there are several relaxations of DP. One important one is what's called epsilon delta DP, which basically gives you this little bit of slack that you can add here. So how can we achieve differential privacy in practice? So here's a few simple mechanisms. So the first one is that we, for the private release of a function value. So if we have a function f of the data set and we want to release that in a differential private manner. The critical quantity here is what's called the sensitivity of f, which looks at what is the maximal difference that if you have a pair of data sets that differ by one entry, what is the maximal difference in the values of this function that you can obtain? And the important thing to remember here that this is really, because differential privacy is a global guarantee, it's not about your specific data set, but it has to apply to all possible data sets that you can imagine. So you really need to be careful about how to evaluate this. But once you have this sensitivity and you can figure it out, then you simply add noise to the function value, scaled by the sensitivity, and also by the epsilon. So basically, the larger the sensitivity, the smaller the epsilon, which smaller epsilon corresponds to stronger privacy, the more noise you need to add. And there's different ways. So if you want epsilon differential privacy, then you can add less noise. If you want, if you're happy with this weaker epsilon delta differential privacy, then you can also add Gaussian noise with a suitable covariance. So that's for computing function values. Then another basic primitive that we might want is to choose among alternatives in a differential private manner. So this could be that you want to find the best something according to a utility. And again, here we need to evaluate the sensitivity for our utility function, which is again a max of max over all possible choices, all possible data sets. What's the maximum difference in the utilities? And then the differential private mechanism here is called the exponential mechanism, which basically samples the R with this softmax type distribution. And again, the smaller epsilon means that the distribution will be more diffuse. And similarly, if we have got larger sensitivity, then in order to retain privacy, the distribution will be more diffuse, and we won't be picking the one top choice, but there will be sort of greater variance in the choices. Okay, so what does this have to do with Bayesian inference, or how could we apply this to Bayesian inference? So the setup that we envision is basically such that we believe that we start from an approach that we have a probabilistic model that we're interested in, that we would like to fit to some data. But this data that we have sits behind this privacy wall, and we sort of want to make sure that this data cannot be leaked. That we will have this differential privacy guarantee on whatever comes out of that data. And so with this, we have the model. We want to fit it in a private manner, perform some Bayesian inference or approximate inference, and really kind of the outcome will be this differential private posterior approximation. So how could we achieve this? There's basically three broad classes of mechanisms that are fairly broadly applicable that have been proposed. The first one is based on using the exponential mechanism. So you can make a choice according to utility. And in this case, you would be making a choice among the parameter values with the posterior probability. And this gives you an algorithm for Bayesian inference. A few other fairly general mechanisms. The first one, the second one of these is what I call sufficient statistic perturbation, is that if you have an exponential family model that has a finite compact sufficient statistic, then you can use the Laplace mechanism or Gaussian mechanism to perturb this sufficient statistic, and then that's actually a very easy and efficient way of performing deep Bayesian inference. Finally, the third general recipe has to do more with approximate inference. So if you have an approximate inference method based on stochastic gradients, either MCFC or variational inference. Then you can again use the Laplace or Gaussian mechanism to perturb the gradients. So I will now quickly go through these different alternatives. So for the first one, posterior sampling, like I said, on some mathematical level, it's really elegant. That, I mean, you simply draw a sample from your posterior. That will guarantee you differential privacy. So you can get sort of beautiful theory out of that, but the practice is often more difficult. So one of the things is that, I mean, in order to use this exponential mechanism, we have to bound the sensitivity, which requires that your log likelihood of your model has to be bounded, or Lipschitz, and over all possible data sets, and this can be sometimes challenging to show. Another thing that, I mean, if you think about this as a means of performing Bayesian inference, then if you have an algorithm that allows you to draw one sample from the posterior, but not more, it tells very little about the posterior. I mean, often we want to know something about the uncertainty as well. So that's a clear limitation. And here, for these methods, you can draw multiple samples, but then there's an additional privacy cost to that, which can be prohibitive if you need many samples. And finally, which is maybe the biggest weakness of these methods, is that the privacy guarantee that we have here is conditional on drawing exact samples from the distribution, which is usually infeasible for most models, and so basically you can't really use MCMC here or anything like that. So it's basically only applicable to very simple models. The second class, the sufficient statistic perturbation, applies for exponential family models, where really, if you've got some data, all the information about that data for the purpose of inference can be summarized in the sum of sufficient statistic. And as I described, then we can very easily take this sufficient statistic and add this noise at the Laplace or Gaussian as was shown. And it's possible to just take this and then perform inference as usual. And it turns out that we can at least get some consistency results for this. So in the limit of infinite samples, this will converge to the posterior, will converge to the non-private posterior, and also the convergence rate that we have for this 1/n is actually optimal for any epsilon delta EP mechanism. So here's one illustration of some work that we've done using this. This is in drug sensitivity prediction using linear regression. This is actually a very challenging problem because so we want to predict the sensitivity of cancer cell lines to cancer drugs using gene expression data. This is very expensive data to collect. So the biggest data set in the world for this problem only has about 1,000 samples, which is very little for differential privacy in general. But nevertheless, by doing suitable learning and using a couple of tricks that I will talk about next, we were able to get reasonable performance. And basically the headline result here is that with the red line here, which is our method, using 800 samples, we get about approximately similar performance as these state-of-the-art non-private methods would get with about 200 samples. So there is a slight price to pay that you need more samples, but if the other alternative is that you don't get any data at all or you get very little data, this can actually be worthwhile. There were some practical challenges for this DP learning, and so especially in the context of Bayesian learning. So one interesting point, if we go back and think about this differential privacy, which basically says that the results shouldn't depend too much. Results of what you really shouldn't depend too much on any single sample. So that basically rules out sharing any kind of latent variables. So if you have latent variable model, you can share the model, but you can't share the latent variables. So that's sort of a limitation you have to then adjust to, and basically, yeah, that's what you need to take into account. In terms of algorithms, I was talking here a bit about this asymptotic efficiency, but of course that doesn't guarantee that it will be efficient in practice for a finite data set. And there's a few gotchas here, which is often these DP methods are highly sensitive to dimensionality. So if you increase the dimensionality, then that often hurts the performance quite a bit. So in order to actually solve some practical problem, you often need to reduce the dimensionality quite aggressively. And that was the case for the drug sensitivity prediction example there as well, that the most accurate DP method has quite a bit lower dimensionality than the best non-private method. Another point is that we need to somehow bound this sensitivity, and sort of the simplest thing you could think about is that, okay, we just take the data set that we have, we scale it down to fit some bounds. But this has the property that even a single sort of outlier point in the data set can enforce a very small scale to all the rest, and basically essentially make the sensitivity very large. And then you need to add a lot of noise in the DP algorithm. So, but these points will not be very useful for learning. So what we have proposed and used for this differential private drug sensitivity prediction is to clip the data, so that we simply clip these very large values to smaller ones. And here's an illustration. So we start at clipping at 2 standard deviations away from the mean, but as we clip more aggressively, the non-private performance hurts a bit, but for the DP that gives a big win. So finally, going for the third approach, so we've got these DP gradient perturbation methods. So the outline of the algorithm is basically such that we assume we have some target function here, split that to terms dependent on every one data point, compute the gradients, these per sample gradients, and then clip those. So this will then give us the sensitivity for the gradient. Stochastic gradients actually help here in the sense that they give you stronger privacy, using what's called privacy amplification. And finally, so we simply add these gradient contributions, add Gaussian noise, and then the total privacy cost. The differential privacy has this nice property that it composes, and there are these composition theorems that tell how you can compute the total privacy loss of repeated applications. And sort of the strongest one of those is what's called the moments accountant. So here's an illustration of this differential variation inference on logistic regression, and it shows that at least on some data sets we can achieve performance comparable to the non-private on with quite strict privacy. And here we were comparing with this a very simple stochastic gradient MCMC method, and at least here the variation inference seems to be doing a lot better. So moving forward, I think there's a few interesting questions that might be, for which this community might make some contributions. The first of which is that, so as I presented these methods, they don't really take into account the noise injected in the DP. So the basic inference is that you add your noise, but then you pretend as if nothing happened. There's been some work, most notably this Williamson and Sherry paper, that sort of proposed methods for taking that into account in the modeling, but it's definitely not very widely used. So there's a lot of room for improvement in this sense. And this links very closely to having the sort of calibrated posterior uncertainty that would take into account, that would incorporate all noise, including the one injected because of DP. And finally, this sensitivity is a key quantity for a lot of these questions, and that is a property of the model. So I think there would be a lot of room for what I would call model engineering, for models that would work well with DP, of course connected with development of inference methods that work well for those models. So with that, I'd like to conclude. So basically, I was talking about DP. has a strong differential privacy, has a strong privacy framework, and the sort of general methods for implementing that, including this sufficient statistic motivation, which really, for finite data, needs to be combined with this really looking at the problem, and so if we want to solve a specific problem, looking at this dimensionality reduction and clipping, and then for more general models, these deeply variational inference and stochastic gradient MCMC. And finally, as a sort of late advertisement, we had a paper in the main conference about how we can combine DP with encryption to use it securely on distributed data. That works well with basically all of these methods outlined here. So with that, I'd like to thank my collaborators, especially Brynal, Honor, Jonas and Arto, who were responsible for the most of the results shown here. Thanks.
Yeah, thank you very much. So, questions? So actually, let me start. So I was kind of curious about this idea of clipping when you have, like, for example, like, I should think of a very simple model like linear regression, and basically when I'm kind of subsampling a data point that has a very strong contribution to the loss function, I'm essentially suppressing that gradient. That's effectively the distribution, if I think about that in kind of modular dynamics algorithm, for example, and I'm suppressing these kind of outliers, that's exactly kind of robust modeling, right? I mean, can you maybe say a little bit more about the connections between robust statistics and in which regard this might help? I mean, you alluded to it in the last slide, but it's kind of very curious.
Yes, obviously, I mean, differential privacy as such, I mean, has a clear connection to robustness, because I mean, you want models that are not overly influenced by one single data point. Yeah, as a method, I think, I mean, the clipping is one very specific means of achieving this robustness, something for which you can perform the inference easily. But yeah, I'm sure there would be room for many other sort of more clever ways of doing that.
All right, thank you. Maybe another question. All right, so let's thank the speaker.